Hey guys, welcome to another video. So today we continue on with calculus area under a curve. So if you haven't already looked at it, already had the first video of the series released last week, and check it out, give it a like, subscribe to the channel if you haven't already done so, tell your friends, all that good stuff. So let's begin. So today the exploration of area under the curve is mainly around questions that involve an area that's enclosed between two graphs. Now, the concept for it, very straightforward, nothing too fancy. So, let me just put down a little bit of theory and then we'll move on to area is what we're talking about here. So conceptually speaking, you have questions that involve two graphs. So one upstairs, one downstairs. So let's say this one here is y equals to fx. And the bottom one is y equals to gx. And then the question basically says something along the lines of, between these 2 points or these two limits, can you please find the area enclosed between them? Sometimes it's between, it'll overlap the x-axis, doesn't make a difference. You'll see that today. All you got to do really is basically take the area. Now I'll rub it off after I do this. You basically take the area under the top graph, right, which represents that pink area there. Yeah, and then you basically minus the area of the bottom here, right? So pink area minus green area to get the black. So formula-wise, we have a formula that basically says area equals to the sum of the limits between the limits of the top area, so fx, the y value of the top minus gx dx. So some teachers give this formula and kids aren't really clear what it is, and just be absolutely clear in this space here. This guy here is the area of the pink. This guy here is the area of the green. We subtract it to get the one in the middle. Makes a lot of sense, guys. So that's the formula. Let's check out. I've got 4 questions planned. The first one, very classical, and the next 3 basically explore similar concept, but with functions that are exponential and trigonometric in nature. So let's check it out. So North Sydney Boys 2014. So classic question where you basically have an area enclosed between two graphs, and in these two graphs, the classical nature of this question is such that there is no, you can see there, they don't give you the points of intersection, which means you solve the two graphs simultaneously, right, to find the points which dictates your limits. Now, it looks like there's one on the origin, but I mean, let's solve them, right? Let's call, if we were to do this with full working out, call this equation number 1, call this equation number 2, right? Because what I'm trying to do is pink on top, green on the bottom. Yeah, once I find those two limits, my area enclosed is the integral between the limits top minus bottom dx, right? So let's see this. So go back to a black. So what do I say here? Sub 1 into 2, right? The simultaneous equations working out. So sub this guy into here. I got x squared minus 1 equals to 2x minus 1, which is great because that's a quadratic, and this one is a really nice quadratic. Minus that over, 1's go away, factorize the x out. It is at the origin, sorry, at x equals 0, then I get a root. Yeah, and 2. And guys, what that means is in the diagram there, that first limit there is 0, and that second limit there is 2. Great. So therefore, right, my area is limits between 0 and 2. Remember, pink, which in this case has the equation of the straight line, that's pink, right? So it'll be 2x minus 1, subtracting the green, which is the x squared minus 1. dx, right? So once you get that, it's a very straightforward integral, right? You basically, let's clean it up before we integrate. Just makes our lives a bit easier. So that's minus x squared and plus 2x minus 1, no, minus 1's go away here, dx. Perfect, integrate that. So be minus x cubed on 3 plus x squared. Limits of 2 and 0. Go over this sign a bit. All right, sub limit. So that, you can sub in 0 if you want to, but I know it's going to be, if you want to show your teacher full working out, fine. So you basically go plus minus 0 cubed, that's 0, plus 0 squared, 0. That goes away. So the answer is 4 minus 8 on 3. What's that, guys? 4 and 3, or 1 1/3 meters, units squared. Nothing too wow about that, right? Pretty classical. And you just got to identify top minus bottom, right? In this case, and it is such a classical part of this question as well, solving simultaneously when the limits aren't given. Now, next question. So this one here, the limits are given. I can see it from 0 to 1. Obviously, then the difficulty now, what school is this from? It's from, it's part of the question smudged out. Sydney Boys 2010. Now, it looks like it's 3 marks in their paper. So I reckon the marks are due to the fact that when you sub in the limits, it's a bit hard because it's exponential, right? So let's have a look. So once again, let's color code pink to be the top, green to be the bottom, right? So then my area will be from 0. Now, in this case, they already told you what the limits are. Great. Pink is this. So E, 3x minus green, which is a concave down parabola. So 1 minus x squared dx. Right, nothing hard about that at all. So then let's integrate. So that one there, there's a 3 there, so I need a 3 in front, divide by 3, so it'll be E 3x on 3. That's minus 1, so minus x. That's plus x squared, so that's plus x cubed on 3. Now, with the limits 1 and 0, makes my life easier if I factorize a third out from everything. Right, so that'd be x 3x minus 3x plus minus 3 because I force factorize a third out. X cubed, the limits are 1 and 0. All right, let's see what we have here. So when I sum in the 1, it'll be e to the power of 3 minus 3 times 1 plus 1 squared minus e to the power of 0 minus 3 times 0 plus 0 cubed. So nothing too fancy right now, right? Pretty basic. So what's that become? Let's see, 1/3 e cubed. I got minus 3 plus 1, that's minus 2, minus 1, so minus 3. Minus 3. Is that right? Minus 3. So checking the solutions. Yep. Solutions look a bit different because they've expanded that, but let's leave it factorized. That is our answer. Units squared. Guys. I mean, 3 marks, 2 unit paper, not too bad, not too bad. I guess the hardest, I don't even know what's hard about this question. The limits was actually easier than I thought. Sometimes they make exponential questions harder by giving you a limit that has logs, and then you start using your log rules and stuff. But that one there, it's pretty straightforward. Quite happy with that one. Guys, let's move on. Sydney girls, now let's do one that is a bit more involved, right? Where looks like there's 2 trig graphs, right? And the area between 2 trig graphs. So is that what they're asking me? Close, yep. So there is the pink and there is the green. And guys, you can see right now there are no limits. Right. So let's say boom, 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 boom. Yep. Points A and B. So that's A and B. Show that A as coordinates and find B. Okay, cool. So they're telling you, right, that when you solve these simultaneously, that's one of the X values and the other one is missing, right? So let's do it. So once again, I will use blue maybe, call this guy number 1, call this guy number 2. So for part 1 in this question, let's solve it simultaneously. Sub 1 into 2. And we get what, root 3 cos x equals a sine x, which is good. Cancel, make that 10 by slotting the or dividing the cos below the sine. So you get sine. Let's do it this way. Let's do it 2 steps. Show working out root 3. Divide the cos then. All right, pretty straightforward. That's 10 equals to root 3. Right, angles of any magnitude, all stations are central. 10 is positive in the first and the third quadrants. So bad to do this, can I shortcut it a bit, right? I'm sure you guys know how to solve this. You get pi on 3 and also 180 or pi plus that. So what's that? Pi plus that's at 4 pi on 3. Yeah, perfect. So it looks like those guys are going to be the two xos, pi on 3 and 4 pi on 3. Now, they just want me to show coordinates, right? So I've got to find the y values as well. So I'm going to say, once you do that, that's probably 2 marks, that's probably 1 mark. And you go, when x equals to pi on 3, you know, sub this into maybe number 2, y equals to sine pi on 3. What's that, sine 60, which is root 3 on 2, isn't it? So therefore, A has the coordinates pi on 3 and root 3 on 2. Similarly, when x equals to 4 pi on 3, y equals to sine 4 pi on 3. Yeah, what's that, guys? Now, using my all stations central angles of any magnitude, I know 4 pi on 3 is in the third quadrant, right? I can see it here. So then the equivalent value is pi on 3, but in the third quadrant, it's negative, right? So negative root 3 on 2 is my y value. Therefore, B has the coordinate of 4 pi on 3 minus root 3 on 2, right? Oops. Maybe I'll just box them individually. Yeah. Pretty straightforward, nothing too controversial about that. All right, nothing too hard. Checking that, perfect. All right, now let's use it. So, I mean, that was all fun. All right, solving trig simultaneously. Okay, fine. Let me just move that up so I have a bit of space to do my integration part, right? Now, so the main game here really is part 2, where the area is between the two limits of pi on 3 and 4 pi on 3, and you can see that there's 3 marks there, right? So it's been involved. So pink graph first, which is actually what, the sine graph, that's the pink one. So sine x minus the green graph, which is actually relating to the cos one, the root 3 cos x dx. And there's my question, guys. Not hard to integrate that. Then I reckon the 3 marks mainly relates to you using your exact values once you integrate. So let's see, integral of sine x. Sine integrates negative, right? The acronym, so that becomes minus cos x. Yeah, and then minus integrates positive, so that becomes sine. That's 4 pi on 3 and pi on 3. Now you just got to work your trig exact value magic, right? So they're both negative. Right, I don't know where the school does this. I'm gonna do it here, right? I said this. I think I alluded to this in the last question. If I force factorize a negative out, right, this becomes positive, this becomes positive, and there's a negative out here. A cleaner way to do this is to get rid of the negative and swap the limits around. Right, that makes life so much easier. So basically, I say this to my students, where if you can factorize a negative out, flip the limit, right? So everything that becomes positive. So cos x plus root 3 sine x, and the limit flips, right? See the last video for the mathematical equivalence sort of demonstration there. It is a thing, right? It can be demonstrated. So let's see. Just makes life a little bit easier, a little bit more manageable when you deal with positive limits. So sub in this guy, root 3 sine pi on 3 minus, so you say root 3, I mean pi on 3, cos 4 pi on 3 minus, no, plus rather, root 3 sine 4 pi on 3. All right. Now I have no more vertical space and I have no more horizontal space. Let's see. I'm going to massage this side by doing this. It's okay. This guy comes here. All right, beautiful. All right, gives me a bit more space to do my exact values. What do I have here? So let's just do it. So cos, that's what, cos 60, that's half plus root 3 times sine 60, which is root 3 on 2 minus cos pi on 3 in the third, so it's definitely negative. Pi on 3, once again, that's a negative half plus root 3, and I think we did this upstairs, that's minus root 3 on 2. Yeah, it feels like it's just whatever this guy's doubled. Yeah? So let's see. So half plus a half. No, sorry, let's just do this. Half root 3, that's 3 on 2. And minus, that's the negative version of that. So it just be like double. So maybe I go minus half minus 3 on 2, guys. So the answer there, the first 2 is 2, the second 2 is 2, so 4 units squared. How is that? Right. So I think the most difficult part of this question is, I don't know. I don't think it's part 1. I think maybe the part 2 with the exact values, right? You just got to remember now, worst case, you can see it's a nice number. People can actually punch it into the calculator and get the answer like from maybe this line up here, but that's how you do it. Nothing too fancy about that question. Guys, I've got one more, right? Just one more, just to demonstrate this area between two curves. Not a difficult concept, just thought I'd show you a few questions, right, and how we go about doing them. One more, Caringbar, 2009. Area between this curve. Now, let's see, nothing, they even gave it to you, right? Sorry, there was no point of intersection, but they gave you the limits. There it is, one above, one below, right? Nothing really hard about this. Both of those integrals are easily integratable, right? Between those limits of 0 and pi on 4. And guys, sec squared, very easily, that's part of your reference paper. Sorry, I didn't even color code it. That was very, very naughty of me. Sine squared x minus x, right? Nothing too hard about that dx. Thought I'd just include another one for a bit of breadth of questions. So that's integral that's 10x minus x squared on 2 with the limits of pi on 4, 0. Arguably, I should have done this question before the last one, but here we go. Guys, what's that? So 10 pi on 4 minus, wow, pi on 4 squared on 2, and then minus 10, 0, minus 0 squared on 2, that's 0, right? And 10 pi on 4, that's 1. And this guy is what? Pi squared on 16, pi squared on 32 units squared. Guys, hopefully that was okay. That's area between two curves. Next week, going to do a video where we're working backwards a bit, where sometimes you're given a graph and you got to derive integrals, etc. Yeah, and then I have one more video planned, I think, where might be combined with next one, I forget, where I cover just different questions, right? Just harder, different questions. I'll see you guys there. So if you enjoyed that video, please give us a like, tell your friends, subscribe to the channel. I'll see you guys later.